All right, let's just jump right in. Today we're exploring how statistics literally transform from abstract, kind of boring numbers into amazing practical tools for decoding the world around us. You know, when we think of math, we usually picture endless equations scrawled on a chalkboard, right? But honestly, math is this living, breathing framework. It helps us make sense of the real, everyday stuff we run into all the time. So get ready, because today, we are officially data detectives.
To kick off our investigation, we've got to ask some real questions about everyday phenomena that math can actually solve. Like, have you ever wondered if you're taller than average for your age? Or, hey, maybe you've noticed that flipping through a tabloid newspaper just feels way faster and easier than reading a dense broadsheet. You might be thinking, is there a scientific way to actually prove that feeling? Well, absolutely there is. By using statistical investigations, we can answer both of those questions with total precision.
So, here's our game plan for today. First, we'll look at investigating everyday statistics. Second, we'll decode percentile growth charts. Third, calculating reading ages. And finally, visualizing cumulative frequency.
All right, on to part 1, investigating everyday statistics. Let's lay the groundwork. The absolutely crucial point here is that math is not just stuck on a page. It's a super dynamic tool we use to analyze everyday life. Statistics basically give us a universal language. It lets us measure, compare, and actually understand incredibly diverse things. Whether we're tracking human physical growth, analyzing how complex a piece of writing is, or spotting massive population trends, statistics provide the exact structure we need to take raw, chaotic data and turn it into clear, actionable insights.
Moving right along to Section 2, Decoding Percentile Growth Charts.
Okay, so when you look at something like the US CDC stature for age charts for 2 to 20-year-olds, you might honestly wonder what all these curved lines actually mean. If you've ever seen one of these, you know they look incredibly dense, just packed with these sweeping curves tracking height in centimeters and inches across different ages. And right at the end of those curves, you see labels like 3rd, 50th, 75th, and 97th. But, what do those numbers actually mean in the real world?
Well, this brings us to our first major concept. A percentile is simply a statistical measure that shows the value below which a specific percentage of observations in a group falls. Sounds a bit technical, right? But think of it like this. If a 16-year-old girl is in the 75th percentile for her height, she isn't just tall. Statistically speaking, she is taller than 75% of girls her exact age in that tracked population. It's basically a really clever way of ranking one individual against a massive group. By isolating these specific data points from those really dense CDC charts, we can easily answer questions about median heights or compare whole populations. For instance, say we want to find the height that 75% of 16-year-old boys are taller than. Well, we'd actually look for the 25th percentile line. Why? Because being taller than 75% means you're actually in the top quarter. Or let's say we want the median height for 12-year-old girls. We just find age 12 on the x-axis, follow it straight up to the 50th percentile curve, since the median is literally the exact middle point of our data, and read the height on the y-axis. Boom! It takes a complex biological process and turns it into a simple coordinate on a graph.
Now, here's a really interesting puzzle. Would all cultures use the exact same height charts? The charts we just talked about are specifically from the United States CDC. If we took those exact same curves and used them for a population in a completely different part of the world, would they still work? To answer that, we have to look past the math. Different cultures and regions have entirely different genetics, diets, and environmental factors, and all of that directly influences human growth. So a 50th percentile or median height in one country might actually be the 75th percentile in another. It just goes to show context is literally everything in statistics.
All right, let's pivot to Section 3, Calculating Reading Ages.
So, let's switch gears from biology to linguistics. We all intuitively know that some texts are just harder to read than others, right? I mean, trying to get through a technical manual feels vastly different than breezing through a comic book. Newspapers, magazines, books, they all intentionally target different readability levels to match who they're writing for. But how does an editor actually measure readability? They don't just guess. They actually use a mathematical formula. Yep, using something called the Gunning-Fogg index, we can isolate a few variables to accurately calculate the reading age of absolutely any text. It's actually pretty simple. First, you take a sample of text and count the total number of words. Let's call that variable A. And then you count the number of sentences, which is variable N. Step 2, you count the complex words, specifically words with 3 or more syllables. We'll call that variable L. Once you have those three simple numbers, you just plug them straight into the Gunning-Fogg index formula. It analyzes the ratio of words to sentences and the density of those big, complex words, and then spits out a specific reading age. How cool is that?
So if we take two different newspapers and run this formula, the math is going to definitively back up our predictions. Let's say we analyze an article from a tabloid. As you might guess, we'd find shorter sentences and way fewer complex words, which gives us a lower reading age, perfect for quick, easy reading on the train. But compare that to a broadsheet newspaper, which usually has longer, winding sentences and super multisyllabic vocabulary. The Gunning-Fogg index will mathematically prove that the broadsheet requires a higher reading age. We have literally just turned language into a measurable statistic.
Moving on to our final stop, Section 4, Visualizing Cumulative Frequency.
For this final case, we're bringing it all together by stepping right into the classroom and becoming the data collectors ourselves. Imagine going around and measuring the heights of every single student in your class. At first, you just have this chaotic, messy list of numbers. To make sense of it, you first group the data into height ranges. Then, you bring in some tech. By dropping this grouped data into graphing software like Excel or Autograph, you instantly produce what's called a cumulative frequency diagram. This running total of frequencies draws out this beautiful S-curve that reveals the hidden patterns in your classroom's heights.
Once that cumulative frequency diagram is plotted, you can immediately grab some key insights, like the median height and something called the interquartile range. Now, we've already talked about the median, right? That's the 50th percentile. But the interquartile range is absolutely vital. It represents the middle 50% of your data points, stretching from the 25th percentile up to the 75th percentile. Finding the interquartile range basically tells you how spread out the most typical, average measurements are, completely ignoring the extreme outliers, like the very tallest or very shortest students in the room. It's seriously a fantastic way to measure consistency.
But here is where the real magic happens. How do we use our shiny new diagram to compare entirely different populations? Well, if you take your class's cumulative frequency diagram and you overlay it with data from a totally different class, say a group of students 2 years older than you, what do you think would happen? You'd instantly see those curves diverge from one another.
The big takeaway here is that graphing software and group data empower us to visually prove differences between groups in literally a single glance. When you plot multiple cumulative frequency curves on the same exact axes, any differences in the median height or how spread out that interquartile range is become completely visually obvious. You don't have to wade through hundreds of raw numbers anymore. The geometry of the curve itself tells you the story. You can conclusively say, yes, this year group is significantly taller, or their heights vary way more, and you'll have the math right there to back it up.
Now that you've seen how numbers can literally decode the real world around us, I want to leave you with a question to explore on your own. We've seen how tracking growth percentiles can map human biology, how a simple mathematical index can quantify the complexity of the news we read, and how creating our own graphs can uncover hidden patterns right in our own classrooms. Statistics isn't just math on a page. It's the lens that brings a blurry world into sharp focus. So, take a look around you today. What everyday mystery are you going to investigate next?